Hello everyone, welcome to this video. In our last video we have learned the mathematical definition of pH. Now let us solve some numerical examples to understand this concept. Let us see our first case of pH calculation when we have been given the concentration of an acid in terms of molarity. Let us assume that we have a 0.025 molar H2SO4 solution with us. To calculate the pH, we need to find out the H plus concentration as per the mathematical formula of pH. In order to calculate the concentration of H plus produced from 0.025 molar H2SO4 solution, we will be requiring two information. First one is about the basicity of the acid. Second one is about its nature. H2SO4 is a strong acid, so it furnishes completely, it dissociates completely, and all of the molecules of H2SO4 will eventually break down into H plus and SO4 2 minus. And its basicity is 2, that is 1 mole of H2SO4 will give us 2 moles of H plus. Therefore, 0.025 molar concentration will give us 2 times 0.025 molar of H plus. We have now the concentration of H plus present in the solution with us. We will simply put this value in the formula for pH calculation. It will give us pH is equal to negative of logarithm 0.05. We can use any standard calculator to calculate this value. However, we can also solve this simple equation with the help of mathematics. So let us get familiar with those steps as well. We can write 0.05 to be equal to 5 times 10 to the power minus 2. Now, in our earlier lesson, we have learned that multiplication within the logarithm can be simplified by converting it into addition of log values of individual terms. So pH will become negative of entire expression within this bracket, logarithm of 5 plus logarithm of 10 to the power minus 2. Logarithm of 10 to the power minus 2 can be written as 2 times logarithm of 10, and logarithm of 10 will be equal to 1. This equation then can be reduced to pH is equal to 2 minus log 5. We can see the value of log 5 from a standard log table, which is equal to 0.70, and on putting this value we can calculate the pH of this solution to be equal to 1.30. Let us move on to our next case, in which the concentration of an acid is given in terms of normality. Let us take 0.025 normal H2SO4 solution. To calculate the pH, we will be requiring the concentration of H plus present in this solution. We have seen the dissociation of H2SO4 takes place as 1 mole of H2SO4 gives us 2 moles of H plus and 1 mole of SO4 2 minus. From the definition of normality, we can conclude that the number of equivalents in 1 liter of the solution will be equal to the normality, which is 0.025 in this case. And from the definition of equivalent weight, we can conclude that there will be as many H plus ions as is the equivalent of the acid. Okay, so number of H plus ions will be equal to the number of equivalents. When the concentration is given in terms of normality, it does not depend upon the basicity of the acid. 0.025 normal HCl solution will give us 0.025 moles of H plus. 0.025 normal H2SO4 solution will also give us 0.025 molar H plus. Okay, so the concentration of H plus will become 0.025 moles per liter. We are keeping the volume in our examples to be equal to 1 liter. Okay, this concept has been explained in a separate video titled as normality. If you are having any kind of difficulty in understanding this relation, I would request you to please watch that video as well. For the time being, we are moving ahead in the calculation of pH. We have got our H plus concentration and we will simply put it in the mathematical formula for pH. Again, following the same steps as we did in our last example, we can calculate the pH of this solution to be equal to 1.60. You can do these steps by yourself, and if you are having any difficulty at any steps, this slide is for your reference. Okay, so let us move ahead and see our next case. Let us take our next case of extremely dilute solution of an acid. 10 to the power minus 8 molar concentration of HCl solution. Okay, so to calculate the pH of this solution, we will again find out the H plus concentration present in this solution. HCl dissociates as 1 mole of HCl will give us 1 mole of H plus ion. So 10 to the power minus 8 molar HCl solution will give us 10 to the power minus 8 molar H plus ions. If we put this value in the formula of pH, then we can calculate the pH of the acid to be equal to 8. However, for an acid, the pH can never exceed 7 under the condition which we have considered in the entire calculation. So this pH is a misleading value. pH equals to 8 is a misleading value. So what are we missing here? Well, when the concentration of an acid becomes too dilute, then we also have to consider the concentration of H plus contributed from the water. Okay, because this is an aqueous solution, we cannot ignore the concentration of H plus coming out from the water molecule, because both these concentrations are now comparable. Okay, 10 to the power minus 7 and 10 to the power minus 8. If we have any strong concentration of an acid, let us say 10 to the power minus 1 molar HCl solution, then we can safely ignore 10 to the power minus 7 molar H plus ion concentration contributed by water. However, in this case, we cannot ignore this H plus ions, and hence we have to sum up these H plus ions. 10 to the power minus 8 moles from HCl solution and 10 to the power minus 7 moles from water. On adding it up, we will get the H plus ion concentration to be equal to 1.1 times 10 to the power minus 7. And now we will put this value in the pH formula, and on solving this equation we will get the correct pH of this solution to be equal to 6.95. So please note, if the concentration of acid is extremely dilute, such as 10 to the power minus 6, 10 to the power minus 7, or any concentration less than 10 to the power minus 7, we will have to consider the contribution of H plus from water as well. Then we can proceed in the same manner. Moving on to our next case, we are now given a weak acid, let us say an acetic acid whose concentration is 0.1 molar. We have to calculate its pH. The difference in the approach with weak acid is that acetic acid or any weak acid does not go 100% dissociation. So the concentration of the acid here is 0.1 molar. It will not give us entire 0.1 molar H plus ion as per the stoichiometry. Rather, the concentration of H plus ion will be somewhat less than 0.1 molar. Okay, to calculate the exact value of H plus ion concentration, we will require an information about the acid. This is represented in the form of ionization constant of an acid. For acetic acid, it is equal to 4 times 10 to the power minus 6. This ionization constant can be related to degree of dissociation alpha. With this equation, alpha equals to root over Ka upon C. This alpha tells us about the fraction of molecules which undergo dissociation. Let us say we have 100 molecules, just 100 molecules in a container, and out of this 20 molecules undergo dissociation. Then alpha will become 20 upon 100. Alright, 20 upon 100. This fraction will be equal to degree of dissociation of the acid. Okay, so now let us go through a general approach to relate alpha with concentration of H plus and apply the same to calculate the answer of this question. Let's say the initial concentration of acetic acid is C. The initial concentration of H plus or acetate ion will be 0. Out of these C moles in a given volume, C times alpha will get reacted or dissociated, okay, because alpha represents the fraction. So alpha times C will undergo dissociation. So remaining molecule will be C minus C alpha, which is same as C times 1 minus alpha. This is the remaining acetic acid molecules in the solution which does not undergo dissociation. If alpha times C molecules undergo dissociation, then alpha times C molecule of H plus will be generated. Now we can put the value of alpha in this concentration of H plus ion here, okay, and we can relate the concentration of H plus ion directly with Ka of the acid. So concentration of H plus will become alpha times C. Alpha we will substitute root over Ka upon C. This will become equal to H plus becomes equal to root over Ka times C. Okay. Now we will use this concentration of H plus to calculate the pH of an weak acid. So we will put the value of H plus in the mathematical formula of pH. pH will be equal to minus log base 10 root over Ka times C. We can simplify it by our exponent relation of logarithm. This root will come in multiplication with the entire logarithmic term here, okay, and we can carry on this manipulation. And now at this point we can define a new term, just like we have defined pH as the logarithmic value of H plus base 10. We can here give this expression a new name, that is pKa. Okay, it has same definition as the pH. Okay, so we can replace this log Ka base 10 with pKa, and this will become our general expression for calculating pH of a weak acid. We will be requiring the Ka value of weak acid. We will take its logarithm and it will become pKa, and log C. C will be the concentration which will keep on varying as per the question. Alright, so from here we can calculate the pH of acetic acid. We can put the value of concentration here, 0.1 molar. We can get the value of pKa by taking its logarithm. So please complete this calculation and post your answer in the comment section. I will also put the correct answer in the comment section itself. From there you can check it out. Now, before moving further, let us summarize what we have learned so far, and this knowledge will also help us in understanding or approaching the calculation more effectively. So, we can now conclude that to calculate the pH of an acid, we require three basic information about the acid, which is its strength, whether it is a strong acid and a weak acid. So how does it influences the calculation of pH? A strong acid will undergo complete dissociation and alpha will be 100%, or in terms of fraction it will be equal to 1. We can be certain that whatever is the concentration of acid, let us say 0.1 molar solution of an acid, then the entire concentration will get dissociated and we will have the concentration of H plus ion to be a multiple of 0.1 molar. We will understand this multiple just in a few minutes. For weak acid, alpha will be less than 1. Okay, so only a fraction of weak acid will get dissociated. The concentration is going to be less than 0.1 molar here, and we require Ka value of acid to calculate any further. Okay, this Ka can be related to alpha, degree of dissociation, as we saw. Then it depends on its concentration. The concentration of an acid can be expressed in terms of normality or molarity. If we know the normality, then H plus will directly correspond to its normality. Okay. On the other hand, if we know molarity, then H plus will be equal to molarity times basicity. So the multiple that we mentioned at this point is nothing but the basicity of the acid. So again, the pH calculation will depend upon its basicity, whether it is monobasic or dibasic or tribasic. Alright, so a monobasic acid will furnish 1 mole of H plus ion per mole of acid. A dibasic acid will furnish 2 moles of H plus ion per mole of acid. Similarly, a tribasic acid will furnish 3 moles of H plus ion per mole of acid. Okay, and this is the multiple that we were looking at when we are discussing the strength. Okay, so we require all this information, and if these information are in our hand, we can easily calculate the pH. Thank you so much for watching this video. In our upcoming video, we will discuss some more cases related to pH calculation. Till then, please keep learning and keep practicing.